Hi, everyone. Thank you for joining. My name is Ben Miller, and I manage the high performance digital and optical portfolio here at Keysight. Today, we're going to talk about something that's becoming fundamental to AI infrastructure performance, and that's validating 1.6 terabit optical modules. As data centers scale to support larger AI clusters, interconnect performance is no longer just about bandwidth. It's about consistency and reliability at scale. At 1.6T, even small degradations in the optical link can directly impact the efficiency of training and inference fabrics, creating higher latency and reduced training throughput. At the same time, updates to the IEEE 802.3 DJ standard to enable 224 gigabit per second signaling have changed both measurement definitions and performance margins. That means the validation approaches that worked for you at 400G and 800G need rethinking for 1.6T. Now, ensuring reliable AI infrastructure now depends on end-to-end validation across the entire workflow, but that starts at the physical layer. So joining me today is Ahmed Al-Chayeb. Ahmed is the Senior Strategic Product Planner and Technical Lead for Keysight's optical interconnect solutions for AI applications. He's an active contributor to multiple industry standards, including the IEEE 802.3, Fiber Channel, OIF, InfiniBand, and LPO MSA. Later in the session, Ahmed will walk you through the latest in optical technologies, changes in the standards, why those changes were necessary, and what they mean for 1.6T transceiver validation. He'll also highlight where existing approaches fall short and what engineers should be doing differently for 1.6T. If you have any questions at all during the session, please put them in the Q&A tab and we'll answer them in the chat. The best questions will be shared with the public chat, and feel free to discuss anything about the webinar in the public chat as well. Finally, near the end of the webinar, you'll be invited to take a survey. Please fill that out. This is your opportunity to let us know what you're working on and how we can help. Make sure to tell us if any of the solutions presented in the webinar are relevant to your projects, and also let us know how we're doing so we can improve our technical webinars in the future. So to get us started, let's level set of where we are and what we're talking about within the AI data center infrastructure. You've likely heard terms like scale in, scale up, scale out, and scale across. These describe how AI infrastructure is evolving to support higher data capacity and throughput for LLM training and inference. Scale in involves increasing performance within each chip with new tech like UCIe chiplets. Scale up is about improving performance within a single server node with tightly coupled compute and memory. Scale out is about connecting nodes across the network to scale distributed compute performance. Scale across is about extending connectivity over long-distance links between data centers using coherent optics. And scale above is about enabling AI infrastructure across a global, edge, and planetary scale with wireless and wired technologies. Now, for today's discussion, we're going to be focused on AI scale out. That's how we connect thousands of accelerator nodes across the data center to work together. This scale-up model is driving the need for higher interconnect bandwidth, moving to 1.6T per Ethernet link, or sending optical and electrical signals at speeds of about 200 gigabits per second per optical lane. Now, to put this in context, we're seeing some issues being reflected across the industry as operators try to move toward faster networks. In a recent survey conducted by Keysight and Heavy Reading, we found that only about 22% of networks are deploying 1.6T today, so adoption is still fairly early, but over 60% of organizations are actively driving network speed upgrades to improve performance. At the same time, more than half of operators are reporting challenges reproducing real-world performance, pointing toward clear gaps in validation and test capabilities. So while the push to scale is very strong, infrastructure limitations and validation challenges are becoming a bottleneck to broader adoption of 1.6T. This is where optical transceivers become critical. Optics have overcome copper as a dominant connection between servers, switches, and accelerator nodes. Despite their benefits over copper, they're increasingly the limiting factor in overall link performance. At 1.6T speeds, you're dealing with tighter signal margins, higher loss, and increased sensitivity to noise and impairments. At 1.6T, failures at the physical layer propagate into link behavior, protocol performance, and system efficiency. So achieving interconnect reliability at higher speeds requires validating performance at every stage, from photonics to electrical to optical to system-level behavior under real-world conditions. Consider how AI training workloads are distributed. These workloads are highly parallel, meaning a job isn't complete until every node in the cluster finishes its task. A single faulty transceiver may not seem like a big deal, but if even a single optical link is marginal, not failing outright, just underperforming, it can increase tail latency across the system and therefore reduce training efficiency. If a link fails altogether, recovery isn't always simple. I just want to really stress this point. Just because it works now doesn't mean it's going to continue to. Thorough end-to-end validation under realistic conditions is essential for proving not just the performance of your transceiver, but the reliability of your device or your end customer's network. At 1.6T, it's not just that the performance margins are tighter, it's the way we define and measure those margins that are changing. To support 1.6T speeds, the IEEE 802.3 DJ standard has been updated to introduce new measurement definitions, new reference receiver models, and new expectations to compliance validation, which means that the test workflow you use for 400G or 800G needs to evolve. With that, I'm going to hand it over to Ahmed, who's going to talk in greater depth about developments in the optical space, including some exciting new transceiver technologies, what's changing in the standard to support these, and what that means for you as you validate your 1.6T devices.
All right, thank you very much, Ben, for the introduction. Let's start by taking a look at the traditional data center topology. Traditionally, data centers relied on copper cable interconnects within the rack to connect switches, while using multimode active optical cables to connect the top of the rack switches to leaf switches, and single mode retime pluggable optics to connect leaf switches to spine switches, as we see in this graphic on the left. However, this topology is starting to crumble under the extreme pressure from hyperscalers and the extreme compute power and bandwidth requirements for AI applications, which is forcing hyperscalers to look for new optical technologies that can address their needs for scaling up, out, and across. So let's take a look at the strengths and weaknesses of each of the existing interconnect technologies. And we're going to take a look at these interconnect technologies from the lens of reach, power, and cost. And we'll start with copper cables. Copper cables, of course, have the lowest power and cost. Nothing comes close to copper. However, they lack the reach required for AI workloads. As you can see in this graphic, DACs are typically used to connect switches within one rack. That stays within the maximum 1 meter reach for these copper cables, and that's good enough for traditional applications in the data center. However, with AI workloads and the rapid expansion in compute cluster size, optics are becoming a need to scale up, out, and across. And this scaling is going beyond the copper cable's reach objective, which is forcing us to use optics. The multimode active optical cables have slightly longer reach that goes up to 50 or 100 meters, which can cover a lot of the scale-up applications. However, it still fails to cover the scale-out applications. And finally, the single-mode pluggable optics will have up to 2-kilometer reach. And in DJ, we actually have a 10-kilometer PMD. However, these optics are considered way too expensive, costly, and they draw too much power. So we need to start looking for new types of interconnects within the data center to address the emerging needs for AI applications. Let's start by taking a closer look at the existing and emerging optical interconnect technologies in the data center. And we'll start with the networking default in the data center, that is front panel pluggable retime transceivers, or simply we're going to call them classical retime transceivers. A retime transceiver includes a DSP PHY chip that retimes, reshapes, regenerates the signal that is driven by the switch ASIC. The DSP cleans up the signal at the input of the T-ROSA, as you can see in this graphic, the transmitter-receiver optical sub-assembly, and that helps with interoperability within the data center. Pluggables are also extremely desirable for their hot swappability, upgradability, and serviceability, making them the default in today's networking. The most common form factors for pluggables today are OSFP and QSFP-DD form factors, which can be either 8 or 16 channels maximum, and that falls short of achieving the faceplate density requirements for these new emerging AI applications. This is primarily the reason why new MSAs are forming to define new form factors. And particularly, I'm talking about the extra dense pluggable optics, or the XPO MSA. So the XPO is a high density 64 channel liquid cooled pluggable optical module that quadruples the front panel capacity up to 12.8 terabit per second per module. Having that being said, XPO is largely considered a mechanical form factor. So the test requirements for XPO are very similar to those of classical retime transceiver, with the added complexity of thermal dissipation, which is the reason why XPO relies on integrated liquid cold plate systems. XPO solves the faceplate density problem of classical retime transceiver. However, it faces the same hurdles that we face with FRO. Next, let's talk about testing a classical retime transceiver. So a pluggable module has 4 interfaces that needs to be validated. On the optical side, we have a transmitter and the receiver, and on the electrical side, we have also a transmitter and a receiver, and each one of those 4 interfaces needs to be evaluated separately. In this webinar, we're going to be focusing on the optical side, so we're going to focus on the optical TX test and the optical RX test, and Keysight does have compliance solutions for both. We're going to talk about that towards the end of this webinar. So let's talk about the next type of optics that we see in the data center. With the rapid expansion of data centers and the exponential increase of optics within the data center, specifically AI compute clusters, it quickly became obvious that the picojoule per bit is becoming the critical bottleneck in the data center buildup. If we look at the graphic that you see here on the right-hand side, you'll see that the DSP is responsible for drawing 49 or 50% of the power in a pluggable module. That is a lot of cost, power, and heat drawn by that DSP alone. This realization led to the emergence of a new type of a pluggable that removes the power-hungry DSP from the module, and that is linear pluggable optics, or LPO. By removing the DSP from the module, LPO solves the cost and the power problem of classical retime transceiver. However, it does introduce significant challenge as it offloads complex signal processing to the switch ASIC. And that poses a particularly hard challenge to solve. So let's talk about testing the optics of linear pluggable optics. On a first look, you would think optical testing would appear to be the same as the test methodology for classical retime pluggable transceivers. However, the specs do say that the relevant optical specifications at TP2 shall be met with any electrical input signal that is compliant. And what that means is we need to achieve the same optical parameters defined for retimed interfaces with an impaired electrical signal at TP1A at the input over here. So this graphic here illustrates the challenge. For retimed optics, we have a DSP right before the optical subassembly, which will regenerate that signal or retime that signal. For a linear pluggable optic, the lack of DSP means that the signal that we're getting at TP1A is an impaired electrical signal, and we still need to pass the same optical parameters defined in IEEE 822.3 specs for retimed optics. This adds an additional burden for testing LPO. This is what the test diagram for testing LPO looks like, because we need to have a precisely calibrated worst case scenario input electrical signal generated and input to this module. In this case, the BERT is used to generate the precisely calibrated electrical input signal, which is then fed to the module through an MCB, or a module compliance board. The optical module output is then connected to a scope, which acts as an optical reference receiver. In this case, the added test complexity is not only to design and validation tests, but also to manufacturing tests. Another critical aspect of LPO is that the lack of the DSP makes interoperability extremely challenging. And that is the primary reason why we're looking for alternative methods. And particularly, I'm talking about the next type of pluggable optics that we'll look at, which is retime transmit linear receive optics, or simply called RTLR. You'll also see people referring to it as half-retimed pluggable optics, or LRO, linear receive only. It's essentially the same thing. And RTLR is a hybrid architecture between classical retimed and linear optics. It essentially uses a retimer for the transmit path. So we see here we have a DSP on the transmit right next to the TOSA, and removes the DSP from the receive path to reduce cost and power. So you see we don't have a DSP next to the ROSA on this RTLR transceiver. From a testing perspective, the presence of a retimer in the transmit path makes testing RTLR, at least the transmitter side, very similar to testing classical retimed optics. Of course, characterizing the receiver is more complex due to the varying host channel losses. So to recap, before we go to the next type of optics that we see in the data center, we talked about 3 different types of pluggable optics: fully retimed, fully linear, and half-retimed optics. And we discussed the strength and the weaknesses of each one. Next, we'll move on to a different type of interconnect. It's not a pluggable in this case. I'm talking about co-packaged optics. So hyperscalers are starting to deploy a new type of interconnect that packages the optics on the same substrate of the switch ASIC or the XPU. Co-packaging the optics reduces power and cost and solves the faceplate density problem. However, it also loses the flexibility and serviceability of pluggables, which is highly desirable. And that adds an additional test burden due to the high cost of failure of co-packaged optics. So with co-packaged optics, you're locked into a single vendor, and any failure is very, very costly. So for pluggables, it was easy to swap out a misbehaving transceiver. However, the flexibility is lost with CPO, which is creating a few hurdles that the industry still needs to solve. And that's why we're starting to see some standardization efforts with the formation of MSAs like the OpenCPX MSA, the OCI MSA, as well as other standardization efforts in OIF and OCP particularly. So testing co-packaged optics and yield are the most 2 critical bottlenecks that the industry is trying to solve today in order for CPO to go to mass deployment. The CPO test workflow starts with wafer acceptance testing and wafer sorting in an attempt to identify KGDs, or known good dies, early on in the process before they get packaged with very expensive ASICs or XPUs in this case. So we start with wafer acceptance testing, we do insertion loss, PDL, optical alignment, process variation. Then we go to sorting, and we're doing frequency domain measurements, DC optical S parameters. Then we go to the third stage, or insertion 3, where we do bare die ATE type testings. And in this insertion, we're doing frequency and time domain measurements. And finally, at the last stage, where we do a CPO module test or a CPO switch test, that's when we're testing the whole CPO module assembled together. And as you can see, the test complexity is increasing significantly as we go from left to right. So it's paramount to try and identify those known good dies as early as possible in the process. The next type of optics in the data center that we're going to talk about is near packaged optics, NPO. And near packaged optics have lingered around for at least a decade or so. However, the need for such an interconnect did not materialize until the AI era. And that's why we're seeing NPO comes back to life. NPO packages the optics closer to the switch or the XPU without being on the same substrate. It often uses sockets for maintainability. So when an optical engine fails, it can be replaced in isolation. Having that being said, that is not an operation that happens in the data center. That's a return to the manufacturer process, which is still very expensive. So maintainability is improved over CPO, but it's not great. It's not as convenient as pluggables. So in addition to that, NPO still needs to deal with short electrical traces connecting the optics to the switch ASIC, which could potentially be even more challenging as we go higher in data rates to 400 gig and beyond. So in summary, NPO opens up the ecosystem for multi-vendor participation, but it does not solve all the other CPO hurdles that we face. And finally, the last type of optics that we're going to talk about is coherent, and specifically coherent light optics, especially in the scale across domain as hyperscalers distribute compute clusters across multiple geographical sites. It is important to note that we have seen significant standardization efforts for coherent optics, particularly the development of a new transmitter quality metric for coherent optics, ETCC, or extended transmitter constellation closure, which is a power penalty TQM analogous to TDECQ in IMDD optics. And that's something we're going to talk about a bit in a few slides. All right, so we have talked about the different types of optical interconnects in the AI data center, but we have not yet talked about how can all these different types of interconnect coexist. The unprecedented demand of AI applications makes it possible for all of these interconnects to coexist, especially with the varying requirements for each application. Standardization is essential to drive broad market adoption and to reduce the total cost of ownership. And while standardization efforts might overlap sometimes, the focal point for our physical layer specifications of optical interfaces has always been the IEEE 822.3 specs. So let's take a closer look at this. It is important to note that all of the different types of interconnects we discussed earlier need to comply with the IEEE 822.3 specs to ensure interoperability in the data center. Now, as we start to deploy 200 gig per lane optics in the data center, all eyes are on the IEEE 822.3 DJ specification that just completed its first Standards Association recirculation ballot in May. Before we dive any further, it's important to note that as per IEEE rules, I must disclose that the opinions expressed during this presentation are my own and do not represent the views or positions of IEEE. So the first concept that we're going to talk about is transmitter quality metrics in 822.3 specifications. Unlike electrical interfaces, optics require tuning, which adds additional testing burden in manufacturing. And that is the exact reason why we rely on complex transmitter quality metrics that aggregate multiple transmitter and fiber impairments into a single metric. The key transmitter quality metric that the industry has relied on since we transitioned from NRZ to PAM4 is TDECQ, or Transmitter Dispersion Eye Closure Quaternary. So what exactly is TDECQ? TDECQ is a power penalty metric that aggregates multiple transmitter and fiber impairments into a single metric that describes the power penalty for the non-ideal performance of a transmitter under test. TDECQ is typically measured on a scope. The scope in this case is used as a virtual optical reference receiver with an equalizer and a decision circuit that the specification would call out in the 802.3 specifications. Now, as I mentioned earlier, TDECQ is something that we've relied on since the early days of PAM4. So since we transitioned from NRZ to PAM4, so the question is, what is new for the 200 gig per lane optics, or for IEEE 802.3 DJ to be more specific? So the first thing 802.3 DJ did is they updated the reference receiver equalizer. Since the early days of 26 gigabaud, 50 gigabaud optical interfaces, we have relied on a 5 feed-forward taps as a reference equalizer. And it's always been maintained that the optical reference receiver is not meant to be a reference design. It's actually a minimum viable reference receiver. It is understood that the actual hardware receiver will outperform the reference receiver. And so this is why TDECQ is pessimistic in nature. Having that being said, the gap between the reference receiver and the real hardware receiver became so significant, it started to call the measurement correlation to link performance into question. And so we needed to try and bridge that gap. In order to do that, IEEE 802.3 DJ updated the reference receiver equalizer to have 15 feed-forward taps and a single decision feedback, or DFE tap. The new reference receiver significantly changes how we optimize the reference equalizer and how we do the TDECQ measurement on the scope. So this is a big change that we need to be aware of when we're trying to evaluate the performance of a 200 gig per lane optical interface. Another big change that was done to TDECQ is a change to the TDECQ calculation method itself. TDECQ has always been defined as 10 log 10 of OMA divided by 6QTR, where OMA, or the optical modulation amplitude, is measured after the reference equalizer. So again, remember, TDECQ is measured on a scope. The scope is an optical reference receiver that has a reference equalizer, and you're measuring that optical modulation amplitude after the equalizer to calculate TDECQ. However, there was always a notion that OMA before and after the reference equalizer would be the same, because that reference equalizer was defined to have unity gain. What we've seen is that for 200 gig per lane signals, that is not necessarily true, and that's because of reflections that might be impacting link performance and not currently captured in the TDECQ calculation method. This is why the IEEE 802.3 DJ CRJ adopted a change to use OMA measured at the input of the reference equalizer to account for the reflections that could potentially impact the link performance. This change will potentially impact the measured TDECQ value, and it's something that we need to be aware of when we try to validate a 200 gig per lane optical interface. So in addition to the two big changes I just mentioned, there's a number of different changes to the corner frequency of the CDR, the precursor limits, the minimum, the maximum, and this is a table that actually summarizes all of the different TDECQ parameters for all 5 PMDs defined in IEEE 802.3 DJ. This table can be used as a reference for anyone who's intimately familiar with the 802.3 DJ spec. However, for those of you who do not want to remember all the intricate details of the spec, rest assured that Keysight will provide end-to-end solution that covers your testing needs, from simulation to design and validation to manufacturing. So as I mentioned earlier, Keysight provides a full suite of automated compliance tests that cover the transmitter and the receiver both electrically and optically. And these are all the different software compliance apps that you can refer to if you're trying to characterize the performance and pluggable module. However, in this webinar, I'm going to highlight the two optical conformance apps. So I'm going to start with the optical TX compliance app, and then we'll move on to the optical RX compliance app. So the N1095 DJCA is an optical TX conformance test software that provides a fully automated characterization workflow for 1.6T optical transceiver that covers almost all of the IEEE 822.3 DJ parameters. That includes OMA, extension ratio, TDECQ, average optical power, transmitter power excursion, REN OMA, so on and so forth. The test app will also allow users to export comprehensive measurement reports that can not only be shared with colleagues internally, but also with customers. So again, if you need a trial license or you want to try out this optical TX conformance test, please do let us know and we're happy to assist with that. On the receiver side, we also have a fully automated 822.3 DG compliance test solution for stress testing an optical receiver, and that is the N4917 DJCB. In addition to the automated compliance software, the test solution includes a Keysight M8050 BERT, an N7718C reference transmitter, a tunable laser source, a VOA, a sampling scope, along with multiple other accessories to connect all of these instruments together and create a turnkey solution to calibrate the stressed eye and test an optical receiver. And with this, that wraps my part for today. I do realize we covered a lot of ground in a very short amount of time, so please do feel free to enter any questions you have for me in the chat or reach out to your local Keysight rep if you want to have a follow-up conversation. And with that, Ben, over to you. Thank you.
As you heard from Ahmed, both the standards and the way we measure optical signals have changed for 1.6T. With increasing complexity, test automation is more essential than ever. There's simply too many details in the specification to keep up with, and they're always changing. And that's just for conformance or compliance validation. Validation as a whole is no longer just a single step. It's a workflow that spans from photonic IC design all the way to system-level performance. It really starts at the component level. As photonic integration increases, design and characterization become critical earlier in the process. Tools for simulating photonic IC designs, as well as high bandwidth measurement and device characterization, like our new 220 GHz Lightwave component analyzer, allow you to validate device behavior and identify performance limits before integration by correlating the measurements with the simulations. At the chip and module level, validation requires running a full set of IEEE 802.3 DJ transmitter and receiver measurements with a high degree of accuracy and repeatability. Keysight test automation solutions cover all of these test cases. The 1.6T optical transmitter test solution, which Ahmed just talked about quite in depth in many different use cases and situations. Those feature our DCAM sampling oscilloscopes, as well as our test automation software, which runs through every test in the current standard and is updated regularly as the standards evolve. Now, these sampling oscilloscopes can be used for R&D and manufacturing testing at scale. We have a 1 and 2 channel option, as well as single mode optical models with integrated clock recovery and precision time base for a complete 224 gigabit per second validation solution. And recently, we launched a multi-mode version of the sampling scope. On the receiver test side, we have our optical receiver stress test solutions featuring our 120 gigabaud BERT, optical reference transmitter, tunable laser source, sampling scopes, and optical attenuator. Considering the increased complexity of receiver testing over transmitter testing, this solution includes a vital software application which unifies instrument control and automates stress signal calibration, receiver sensitivity, and jitter tolerance measurements. But even after you achieve compliance, your validation isn't complete. At these speeds, performance at the individual lane doesn't always translate to system-level behavior. And that's why you need solutions like our functional interconnect test system, which enable BER and FEC validation across multiple lanes under realistic conditions. This helps identify issues that don't appear on isolated lanes or post-FEC. We have the FITS or FITS system for receiver testing, BER, and post-fact, as well as our interconnect and network performance tester, which takes things up a level by testing interconnects and modules under realistic traffic conditions at layers 2 and 3. Finally, validation extends to the network itself, which tools like AI Data Center Builder and Inference Builder, you can emulate real AI workloads across distributed infrastructure. This allows you to see how interconnect performance impacts latency, congestion, and workload efficiency before deployment with realistic workloads. At this stage, you're no longer just validating devices, you're validating the behavior of the entire AI system and optimizing it accordingly, whether you're doing a backend system for training or a front-end system for inference. As I said, at 1.6T, passing compliance is just the first step. Ensuring reliable AI infrastructure requires validation across the entire workflow from photonic components all the way to the system-level performance. Because ultimately, success isn't measured by passing a test, it's measured by how robust your systems are and how they perform at scale. So, before we wrap up, let me leave you with a few takeaways from today's sessions. First, as AI infrastructure scales out, we're seeing a fundamental shift in optical architectures, from traditional pluggables to LPO, CPO, XPO, and beyond. And each of these introduces new constraints and new validation challenges. Second, at 1.6T, optical fiber performance is right at the edge of what's possible. The margins are extremely tight, and even small impairments can quickly translate into system-level issues. Third, IEEE 802.3DJ changes how we define and measure performance. It's not just incremental. Measurement models like TDECQ and the reference receiver have been updated in ways that directly affect results. Validation approaches that worked at 400G and 800G don't reliably carry forward. In many cases, they simply won't correlate at 224 gigabit per second speeds, so you need to update your methods and your test tools. And finally, all of this points to a much bigger shift. Ensuring reliable AI infrastructure now requires end-to-end validation, from photonic components to PHY compliance to link behavior, all the way up to system-level performance under real workloads. Because ultimately, success at 1.6T isn't just about passing your tests, it's about ensuring your system performs reliably at scale with end-to-end validation. Keysight is proud to be the mission-critical design enablement partner of you, our customers, who are solving the world's most complex engineering challenges. It's thanks to our measurement scientists and our industry standards experts like Ahmed that we can offer such a range of great solutions, but also to partner with you and to help you through each and every step and every challenge of your development and validation process. Now, if you're developing photonic ICs, transceivers, interconnects, networking equipment, or even architecting entire AI data centers, please fill out the survey. The Keysight representative will be in touch soon. And that's our webinar. I'd like to thank Ahmed for joining and sharing his expertise, and I'd like to thank all of you for tuning in. I hope we got to every question in the chat, but if not, we will be in touch and we'll follow up with each of those. Also, feel free to download the files in the handouts tab before you go. And don't forget to fill out the survey, and we'll be in touch with you very soon. Thank you so much.